Hello everyone, this is Professor Rakesh Singh Satramayan from Indian Institute of Technology, Guwahati. The title of our paper is Ultra Thin and Conformal SSPP based ultra wideband low pass filter for beyond 5G radio strip network applications. My co-author is Ms. Sunanda Lakim Sethi. So there's a technology called CellFree massive MIMO, which is actually a beyond 5G technology, and it is proposed to be used for 6G wireless communications. So in this technology, we'll actually distribute the base station antennas to many access points. And in any geographical area, it will be surrounded by many access points. So looking at any of the user equipments or mobile user, it will be always surrounded by access points. For example, if you consider the mobile user 1, is the mobile user 1 here, it will be surrounded by access point 1, 2, 3, 4, and so on. So this user can actually communicate to the nearby access point, and those signals will be actually transferred to the CPU and through the front haul networks, and CPU will do all processing. So the basic idea is when you distribute the antennas at the base station to many access points, will have huge diversity gain at the base station side also. Because of that, there will be a huge improvement in the performance. So in such kind of scenario, there's nothing like shells. The concept of cell will be freed. And it's the best situation for the user. User will be always surrounded by access points. So the idea is you have to have so many access points in a geographical area. So the technology which will enable this cell-free massive MIMO is actually proposed by two scientists and engineers at the Ericsson, Sweden, Paul Frenger and Jan Heredent, somewhere in 2019. They call this as radio strip networks. As you can see here, radio strip networks actually looks like a sellotape. So all the circuits will be printed on a very thin layer like a sellotape. It can be rolled out, it can be stick on any surface. So this is very easy to implement. This radio strip networks are very easy to implement, and it will enable 6G wireless communication technology like cell-free massive MIMO. So if you want to implement cell-free massive MIMO, you need to have a technology which should be easily rolled out because you have many access points. So if you use a technology which will be very difficult to implement, then it will not be very successful. So in order to have a very successful cell-free massive MIMO implementation, radio strip network is the technology which will enable such kind of implementation. This can be easily seen from few examples we'll be discussing in the next slide. The first example is radio strip network application in public transport. The public transport, you can see that there are many passengers here holding mobile phones here. They're doing some kind of thing, some kind of communication with their mobile phones, and there will be huge traffic here. So in order to provide very good quality of service and data rate to each and every user, there should be some radio strip networks inside the public transport also. So in this diagram, it can be seen that on the doors of the public transport, on the floor of the public transport, there's a radio strip networks. Even on the walls and windows, there's radio strip networks. So it will actually enable very good quality of service for each and every user. Similarly, another situation is when you consider train station. In the train station, there are many users waiting for the next train to come, and each user is having a mobile phone. So there will be heavy traffic here. In order to give good quality of service and high data rate for each and every user, radio strip networks can be put on the walls of the train station, and it can also be put on the rails of the train station. Similarly, another situation is when you are in a city square. There are many people walking on the city squares. It's a hugely crowded area. So the solution for providing good quality of service and high data rate for each and every user is we can actually exploit the packets of the building. So the packets of the building, we can put radio strap networks. Similarly, in the airport terminal, also we can put on the walls of the airport terminals, we can put the radio strap networks. Another situation, this is actually auditorium for Indian Institute of Technology, Guwahati. So usually auditorium is very crowded. There will be many users with mobile phones. So in order to provide very good service to each and every user, we can actually exploit the walls of the auditoriums where we can put the radio strap networks. Similarly, outside the auditorium also we can put radio strap networks on the faces or facades of the building. Another situation is this is the girls' hostel in Indian Institute of Technology, Guwahati. So on the walls of the hostel, we can also put radio strap networks to give very good service to each and every hosteler inside the hostel. So there are many situations. So we actually want to roll out these radio strap networks for CellFree massive MIMO on the existing infrastructure. So it should be very easily implementation on the existing infrastructures. We have taken so many examples now. So this is the first paper on the radio strap networks. It actually claims that we can have ubiquitous communication almost anywhere, everywhere. And this is the second paper, and it discusses about the circuit implementation of the radio strap networks, how circuit will be implemented in the radio strap networks. This diagram actually gives you an idea. So radio strap networks has CPUs connected with many access points. Many access points are connected with antenna elements, and many processing circuits are also there. So this would be like a sequential circuits printed on a very thin layer, which I have already shown you at the beginning. But then the inventors actually do not disclose how to implement this radio strap networks. They have just shown that radio strap networks will be like sellotape. It can be rolled out. It can be stick on any surface, wall, buildings, or any vehicles, but they have not disclosed how to do it. So we are actually proposing a technology for implementing radio strap networks. There's something called suppressed plasmon polaritone, which actually exists at the optical frequency. These are electromagnetic waves that travel along a metal dielectric or metal air interface at the optical frequency. And such kind of similar behavior has been observed at microwave frequency. It's called spoofed surface plasmon polaritone by Sir John Pendry from Imperial College London. An extension of this work, actually, Professor Sway and others actually proposed in 2013 that we can actually make conformal surface plasmon polaritone structures. So this kind of surface plasmon polaritone structures are conformal. It can be actually made conformal to any surface. So our idea is, why not we use this idea and implement radio strap networks, because this can be rolled out, this can be stick on any surface. Same idea we have for the radio strap networks. So this conformal SSPP structure can be used for implementing radio strap networks. So we have taken up one example of ultra-wideband low-pass filter, which is ultra-thin and implemented on a flexible substrate. And we propose this for beyond 5G radio strap network applications. This is a unit cell of the structures. You can see that dimensions are given by H, A, W, D, and P. We actually took some specific dimensions in millimeter, which are listed in this table 1 here, and plotted the K beta diagram. What we observe is that the K beta diagram for this proposed unit cell is below the light line. So it's a slow wave structure. And it will be able to support the SSPP waves. And another thing we need to worry is that microstrip waves and SSPP waves, there should be a conversion from one to others, and without minimal reflection, because we are designing a low pass filter here. Any reflection within the passband is actually unwanted. So we have a convergence section here. We actually slowly vary the height of the metal printing here from the microstrip line with zero height to the height of the SSPP structure. So this is the convergence section at the input side. This is the convergence section at the output side. It slowly decrease the height of the metal printing. And this is the SSPP structure region here. This is the side view, and in the side view, you can see that we have this kind of structure in top and bottom surface of the substrate. One surprising observation is that we don't need any ground plane for SSPP structures. And we have observed the performance by doing a simulation, commercial software simulation, and it has been observed that this has a very high cutoff frequency around 12.06 GHz. And the maximum rejection level is around 65 dB at 13.6 GHz. So around 13.6 GHz, it has a rejection level of 65 dB. Return loss inside the passband is below minus 15 dB. And insertion loss is less than 2 dB. So it's a very good low pass filter performance. Return loss is 15 dB and insertion loss is 2 dB. So the bandwidth is from 0 to 11.96 GHz. We have also looked at the passband group delay, and it's having a very flat response, and which is desirable, and its value is around 0.7 nanoseconds. So this is a proper ultra-wideband low-pass filter. We have done a parametric study of this kind of low-pass filters, SSPP-based low-pass filter, and it has been observed that by changing H and W parameters, we can actually change the cutoff frequency of this low-pass filter. And we have also varied W and D, and we can see that it can reach cutoff frequency up to 22 GHz. Our design filter cutoff frequency was around 12.06 GHz, but we can even increase this cutoff frequency up to 22 GHz. But then the rejection level will actually be reduced. So there's a compromise in the performance here. The rejection level in the stop band is reduced, and you can still increase the bandwidth of this low pass filter. It has been observed that you can even change the bandwidth by changing W of the filter. So we wanted to have an observation on the wave propagation inside our low pass filter. So we did a simulation and found out that electric field distribution at 6 GHz, you can see we have SSPP modes propagating inside this structure here. But when we do the simulation of electric field distribution at 12.2 GHz, which is outside the passband, there is no wave propagation. SSPP mode propagation has been stopped. So wave cannot propagate beyond 12.2 GHz. This actually validates our idea that SSPP modes are propagating inside this kind of low pass filter. So as usual, we actually make a comparison of our filter with the existing filters in the literature. And it has been observed that the return loss is highest for our low pass filter, which is greater than 15 dB. Another thing is that the rejection level at stop band of 13.6 GHz is around 65 dB, which is highest among all the reported filters in the literature. So the most important part is that all the reported filters in the literature cannot be used for radio stripe networks because they are not conformal. Our filter is designed on a flexible substrate, polyimide substrate. So it can be rolled out, it can be folded. So it's a conformal structure, and so it can be used for radio stripe networks applications. These are references. Thank you very much. And if you have any question, please feel free to ask.